I want to spend a few minutes talking about magnetism, which is found in chapter 8 in your book. One of the first things I want to talk about is the fact that magnetism is real similar to a lot of the properties that we discussed in the electricity chapter. And besides the fact that you have played with magnets probably all of your life, so it's very familiar to you. Magnets actually have been known for centuries, and the Greek culture and the Chinese culture actually used magnets because they had magical properties, and they used them for their rudimentary compass, and it was a rock called magnetite. And if you've ever been to any place that sells rocks, I know there's some like at the Flying J at McCammon, they have magnetite. It's kind of a blackish, grayish rock. And what does it do? It acts like a magnet. And so it was used as a compass in early centuries until we have upgraded to what we have today. Now, actually determining that the Earth is a magnet happened in the 1600s by an English physician named William Gilbert. And what he proposed is that the Earth would have to be found to be a magnet and have magnetic poles, because he discovered that the Earth had iron, cobalt, and nickel in it. Now, the only magnetic materials naturally are iron, cobalt, and nickel. That is what is attracted by a magnet, and that is also the only materials that a magnet can be made out of, which is the iron, cobalt, nickel. Now, you found when you did the static electricity lab that you could make some temporary magnets out of balloons or out of straws or out of plastic cylinders, but the actual permanent magnets are made from iron, cobalt, and nickel. So what is magnetism? Magnetism simply is a force of attraction or repulsion of a magnetic material. So any kind of attraction or repulsion of a magnetic material is found to be magnetism. That's what our book definition is. And how you can tell that something is magnetic, well, if you look at the little diagram, it shows you that there is a north and a south pole, and at the poles it is actually has the most magnetic attraction or repulsion is at the poles. So if you look at the diagram, and you can actually see right here the lines of magnetism, they're much closer at the pole, and as you move away from the pole, they get farther apart. So magnetic force, that's a force that you feel when you bring the objects together. So if you have a bar magnet and you put the same pole, either north and north or south and south together, you can feel a little push. That is the magnetic force. And we know that like objects repel. So north and north would repel, south and south would repel. And we also know that opposites attract. That's a no-brainer. We've learned that a million times. Another thing that is pretty familiar, but I need to clarify for everyone, is that poles of magnets always come in pairs. You can't just have a north magnet and a south magnet. Each magnet has a north and a south. They always come in pairs. So what happens if you cut a magnet in half? Well, you basically now just have two magnets. You get two smaller magnets, each having a north and south. We also want to talk about magnetic fields. If you'll notice, there are magnetic fields around any kind of magnet. And that magnetic field is what surrounds it and exerts the force. So we've talked about magnetic force, magnetism, magnetic field. Next, I want to talk about magnetic domains. Okay, domains are the properties inside the atom where the electrons are spinning, and you have magnetic domains. This graphic kind of shows you what I'm talking about. Within each piece of material, let's say just a bar of iron, you have all these different domains. So you have within the domain, like within the yellow domain, everything's going the same way, but in the purple one next to it, they're not. But everything in the purple domain's going the same way. The red domain, it's all going the same way. So you have all these different domains together, and they're kind of scrambled. When we magnetize something, we actually have all the domains going the same way. So when you have all the domains going the same way, then that's when you end up having a north and a south. And that's why if I were to cut this right in half, you would still have a north end and a south end, because you get all those electrons going exactly the same way. Now they make magnetizers. I actually used to have one. It was a little machine, and you could put a little bar of iron, cobalt, or nickel in it, plug it into the electrical outlet, turn it on, run some electricity through that piece of iron, cobalt, or nickel, and it would cause all the domains to line up, and then you would actually end up with having a magnet. You could magnetize something. You could magnetize a paper clip. Anything that was iron, cobalt, and nickel, you could stick in it and magnetize it. So that was kind of fun to play with it. So just another graphic to show you when something is unmagnetized, it looks all scrambled up like this. And when it becomes magnetized, it looks very straight and very orderly. It's like little soldiers in a row. So how do you break a magnet? How do you get a magnet to not work any longer? If you've ever had magnets that are on the front of your refrigerator and you've dropped them, that will cause the domains to scramble again. So it's no longer magnetized. So if you have a weak magnet, it's usually because it's been dropped or it's been next to something which has caused it to demagnetize. The other thing that's really easy to do is you can heat it up. If you heat it up, we all know from studying this before, when you heat up things, they expand, the molecules in it move faster. So once again, you would cause those domains to scramble, and there you go. You now no longer have a magnet, you just have a piece of metal.